Is my screen visible?
Yes, it is visible. Yes,
Okay.
now full screen. Okay, okay.
Okay.
So
So
thank you, Prasenjit, to to start giving us time for deliberations for our workshop. So one warm welcome to our workshop session. So this is our second session of day 5 program or event. So he's an assistant professor of computer science department of NIT Rourkela. I'm requesting him to start the session. Thank you, Prasenjit. Please carry on.
okay. Thank you. Thank you so much for this warm welcome. So today I'm going to talk about how CNN kind of application can be applied on electric vehicle, as well as I will light upon certain applications which can be applied in the electric vehicle only, which we cannot apply on motor vehicle. So let us talk what are first what are the application areas in electric vehicle, how we can do some advancement related to machine learning in electric vehicle, and after that I will show some application of CNN on computer vision applications on electric vehicle which can be made autonomous. So, let us talk about the Google car. So, as we can see in the Google car, there is a camera there, 360-degree rotation camera is in there. So, this camera can detect whatever vehicle is coming from behind, front, left or right. It can detect it, and accordingly it can control the vehicles so that it cannot make any adverse situation. Now, as electric vehicle having some energy, battery power is there, so this camera and all the computation system can be worked with the help of that energy or charge, which we cannot do in a normal motor engine vehicle, because they are basically not driven by batteries. So we need some explicit battery sources to do that. But here in electric vehicle, as batteries is already there, energy is already there in the machine or the vehicle, we can use that energy to achieve this success. Like if there is no driver, then also it can drive hassle-free, and that is why it is sometimes known as autonomous vehicle. So it is easy to make an electric vehicle to be an autonomous vehicle, whereas for an engine vehicle, it will be difficult, because in that case, we need to explicitly import a huge amount of battery, which will adversely affect the size and weight of the vehicle, as well as it may also come up with some safety risks. So based on that, there is a concept comes that is called advanced driver assistance system, that can provide like lane departure warning, whether I am departing from my lane or not, forward collision, if there is any vehicle coming in front of me, or if there is any pedestrian crossing in front of me, or if there is any child running in front of my car, all can be detected, and accordingly car can control itself, like whether it should press a brake or not, or whether it should slow down or not, or whether it should move left or right, to avoid the collision. That decisions can be made on the runtime in the fly, so that it can avoid any kind of forward collision. Similarly, pedestrian detection, automatic emergency braking, what I just told, adaptive cruise control can be achieved. And these all can be achieved in an electric vehicle because there is already battery installed there. And that energy we can use to charge our cameras and all equipment sensors, as well as we can run a small computer which will deal with all the data received by the sensors, so that it can act upon it. Like in any, we can think of it as an AI system. So AI system means what? It builds on the concept of PAS. Like there's a P for performance, E for environment, A for actuators and S for sensors. So what I am in here talking about, like electric vehicle. Electric vehicle, we want to make it autonomous, like it can work without the driver, or it is going to serve the driver to make it more safe. That means our objective is to reach a better performance. So here we want to incorporate AI as well as machine learning into our EV vehicle. So what is AI? I want to achieve better performance. That is the first goal of any AI system. So performance means with respect to safety, with respect to performance means like it should detect whether there is a chance of collision or not, the departure is there or not. I should reach my destination in a smaller amount of time. I should take care of the conditioning of the car, like the car should be warm and ambient temperature should be there so that the driver feels comfortable if there's any driver. So all this performance need to take care of. Second thing is that E for environment. So the driver or the vehicle should adapt to the environment. Based on the behavior of the environment, the car, the automatic vehicle, autonomous vehicle should learn itself and modify itself. So if it's seeing that it is running through a road where too many kids are playing, so it will be very much cautious while driving. And if it is driving in a highway, it can think about the other performance rather than whether there is a chance of any pedestrian or any child is running in front of the car or not. The chances is very less if it is driving through a highway. So in that case, it may consider like what will be the optimal speed so that it can reach its destination in time. So the performance varies depending on the environment. So environment is another factor in any AI system. Third one is the actuator. And before actuator, I think I should talk about the sensor. So A and S. So PEAS. These are the epitome of any AI system. So ACE is the sensor. Now sensor can be any sensor like electrical sensor that is going to assess what is the ideal temperature, or what is the wind speed, and many other like the humidity like that. So similarly, the camera can also be, okay, give me a minute, 1 second, sorry. So yeah, I was talking about AS. Sensor can also be like sensor decision. So can consider a sensor. And fourth one is actual. Like I need to act upon. After seeing something, I need to act upon the environment. Like whether or should or move to the left right direction. These are the actions I am going to take upon the environment. So that is called A. So PEAS is the one of the vital thing in any AI system, so that we can achieve in autonomous vehicle or any electric vehicle if we can upgrade it. So cameras placed around the vehicle can continuously monitor the environment, detect the object and obstacles, and provide alert or assistance to the autonomous drive. Now, parking assistant, it can also provide parking assistance, like it can aid in parking by providing a 360-degree view around the vehicle and helping the driver maneuver into a tight space accurately. Similarly, it can also help in a navigation systems like which road there is a congestion, which road may have been more traffic, and which road there may be a chance of less traffic, which already the Google Map provide while we drive by any Uber or Ola. So it can use the GPS signal to know that which road is unreliable and reliable. Those things can be taken care of. So it also helps in enhanced navigation systems. Fourth is battery management. Like if there is an overheating in the battery or not, that can be sensed by a temperature sensors or any heat map by the camera, and it can assist that whether we should stop the car or not. So in a battery management also, there's a huge implication of AI as well as ML. AI means I already discussed that PAS principle. That means performance, environment, actuator, and the sensor. Similarly, suppose there is the charging station. We may have seen these in many advanced documentaries. Like if you just go through a charging station for electric vehicle, it can automatically detect the port where it need to charge the electric vehicle. So accordingly, if there is no person or assistant is there in the charging stations, then it can automatically detect certain equipment, and maybe there may be a robot that is going to do the job of charging. So that plug and cable management can also be done automatically. So the challenge is that like that the advanced object detection recognition algorithm is there, and the thing is that whatever decision we are going to make, that decision we need to make in a runtime. So there should not be any latency. That is a big concern in case of computer vision in autonomous vehicle. Let me try to discuss in a better way. Suppose you detect a child is running in front of my vehicle. Now my camera will take the picture, send it to a computer. Now computer detect, yeah, there is a child which is running in front of my vehicle. It detected. Now after detection, it needs to let the computer, or in our case the vehicle, know that we should press the brake or we should slow down. So we need to make a very quick decision. We need to quickly judge in the runtime whether there is a child running or not, or whether should I press the brake or not. So the decision need to be done as fast as possible in a real time. It is not like that I'll make a decision and let it know after 2-3 minutes. It will be long delay. So that is why your it is not like that your cameras will collect all the information and send the data to any cloud like Amazon, AWS, and all, and it is going to pass the information. The computational facility, at least a minimum computational facility, should be there in your vehicle. That is one limitation. Yes, there will be latency or delay, which can affect the performance or delay in the performance. So that is a big concern. Now, how much computational facility we are going to provide in a vehicle, that is a area where we need to trade off. If we give too much computational power into that vehicle, then it will come with a lot of price, as well as how we are going to manage that computing system into that vehicle. It will also affect the size and the shape of the vehicle. So those are the things which we also need to consider. Whereas if we want to provide minimum computational facility to the vehicle, in that case, all the data cannot be processed in the runtime, so it will go to the cloud server. Cloud server, and there may be a network issue, because it will take a lot of time to send all those data to the cloud computer. Then cloud computer again make a decision and pass it to the computer. So the network latency comes into the picture if you use the cloud computing. So it is so edge computing is a concept where the computer is there in the sensor, which I suggest, but it will be a lot costly, and it will be difficult to implement in a car. And another concept is that cloud computing, it comes with a network delay and the computational delay. So that is another issue with that. So sometimes we come up with a concept called fog computing that I am not going to discuss in detail, but fog computing is a concept like little workload will be there in your system like vehicle, and most of the hard working job may be done in the cloud. So it is a trade-off between edge computing and a cloud computing. So that kind of concept can be imported to come up with a better EV, which can be made AV, autonomous vehicle. So these are the real life examples where EVs are made AVs, means electric vehicle are modified into autonomous vehicle. Examples are Tesla Autopilot, Neo Pilot, BMW iX. These are the real life examples which are currently in use in the market. So this is the Tesla Autopilot. It can detect any vehicle, its shapes and type of the vehicle, and accordingly it can adjust the autonomous vehicle so that it can avoid any kind of adverse situations. Now, if we want to build any autonomous vehicle, what are the steps we need to consider? First of all, we need to take care of the system architecture. Architecture means on which vehicle we want to import it, how many sensors will be there, will there be any motion sensor or not, camera setup, what are the places, optimal places where we need to place the camera. So some computational geometry concept comes into the picture. After that, many computer vision algorithms we need to know, and we need to know which computer vision algorithm are appropriate on my situation or the data. Functionalities, I need to take care of which functionalities. I want to do the automatic parking, or I want to take care of battery management, or I want to take care of the navigation. So based on my objective, the data set will vary, and accordingly, my computer vision algorithm will also change. After that, we'll do the lot of training, and if it pass the safety guidelines, then we can import that concept into any vehicle. So that is our objective. Now I am going to light upon certain factors like how a image is treated by a computer, and how, suppose a child is running in front of my car. So first of all, my camera will detect the image which consists of a child in an road. So obviously, my first job is to detect the object, the child, in the image. That is the very teeny task or an important task in my computer vision, maybe crux of computer vision, to identify the object in the image or in the video. Now we all know that video is nothing else but a set of image. So if my video is like 30 frames per second, it is nothing else by, in a 1 second, 30 image I am basically passing very fast. And as we know, our eye cannot detect difference if there is change in the pictures within 1/10 of the second. It see as a continuous moment. So in this example, if your video is 30 frame per second or 60 frame per second, that means 60 or 30 images we are going to use in each second. So that is why video is also nothing else but the motion picture, the picture in motion. So let us see how we can detect any object in an image. So as we can see, this is an image, the image of the very famous image in the computer vision technology. There is the image of Lena, and as you can see, the image are consist of lot of pixels. Now these pixels may have any value, but we normalize it and call it a grayscale image. So what is special about grayscale image and why it is called grayscale? So an image is consist of lot of pixels positioned both vertically and horizontally, and each pixel having a value which can be minimum 0 and maximum 255. Now 0 means it may be a complete white pixel, and 255 may be a complete black pixel. Or you can consider the opposite scenario, like 0 means completely black pixel, and 255, which is the maximum value, that means the white pixels. And in between them, there are various shades of gray color exist. And that is why it is called grayscale image. So various shades of gray are there in between low value 0 and the max value 255. And why this is precisely the range is 0 to 255, or overall 256 shades of gray are there. It is again, there is a computational concept there behind. Like we all know, in a computer, data stored in a binary form, like data stored as 0 or 1. So a particular bit in a computer store either a value 0 or 1. So if we have 8 number of bits, then they can store 256 data. Let me try to use a pen. So suppose you have a 1 bit. It can store two different type of values. The value can be either 0 or 1. Now if I have 8 bits, so each bit can represent two different possibilities. So how many total possibilities can be represented by 8 bits? It will be 2 to the power 8. These are number of permutations possible if we have 8 bits. This is bit 1, bit 2, bit 3, bit 8. So these are 256 values, and that is the reason we use. So the range is, if the number of possibilities are 256, then the possibility lie in the range from 0 to 255. So we can dedicate one byte. We can dedicate one byte for each pixel. So obviously the image, if the image is 30 cross 30 image, like 30 rows are there, 30 columns are there. If the image is 30 cross 30, then how many byte I need? I need 90K, sorry, 9K, or sorry, I need to erase it. 1 second. So I need 900 bytes of memory. So for each image takes 900 bytes of memory. Now if I want to consider a video, like one video which having 30 number of frame per second. So one video having 30 frame per second, and this video is suppose 15 seconds video. Suppose you are having a 15 seconds video and each frame per second is 30. So how many image will be there in this video? So the video is of 15 seconds. So 15, and each second contain 30 frames. So 30. This will be my number of images, and each image contain 900 bytes. So overall, this much amount of storage I require to store my video in a computer. And on it, I need to apply some algorithm to find out whether in this 15-second frame, there is any child running in front of my camera or not. So this is the overall goal to achieve. Now, reality, the image cannot be only black. The image can be colored image. By colored, what does it mean? So it means, 1 second. So instead of the pixel having a single grayscale value, now the pixel can have a 3 different types of values. Like it can have a value with respect to the red component. It can have a value with respect to the green component, and it can have a value with respect to blue component. So as we know from the chromatology, that any color can be generated in this world with the help of these three fundamental colors: red, green, and blue. So by mixing up these three colors, I can generate any colors from the darkest one to the brightest one. So in a computer vision technology or any camera technology, we use three channels: one with respect to the red channel, one with respect to green, and one with respect to blue. And based on the combination of the red, green, blue, we can generate any color. So the color image sometimes are represented by the RGB model or RGB channel. So as we can see in this pixel, maybe this is the pixel. So here the red value is 89, green value is 32, and blue value is 77. So in that case, each pixel having three values. Now, this pixel again can be represented with, earlier the pixel was represented with how many byte? Earlier a pixel was represented by 1 byte. Now the pixel is represented by 3 byte. And suppose there is a 900 pixels are there in the image, 30 cross 30 image. So, and if the video is of again 30 frames per second, it will be multiplied with 30. And if the video is of 15 seconds, then it will be multiplied again with 15. So overall, this will be the storage space required to store that video in a per second increases, or the video duration increases, or the resolution of the camera increases, it is going to increase the storage space required to store the data in a computer. Now, if your computer cannot be large enough, which can be accommodated in an autonomous vehicle, then obviously you should work with a low resolution camera. Now, in any good classifier, like now my job is to identify whether there is any child in front of my car or not. So the camera of my car needs to detect any object in front of or obstacle in front of my car. So if in front of my car there is any child, any pedestrian, any very nearby vehicle is there, I need to detect it. That is my first job. Now, it doesn't matter where the object is. Like in an image, the object can be placed anywhere. Like this is my image. Now, object can be in here, object can be in here, object can be in here. It doesn't matter where the object is. If the image captures the object, that object is present, it can be in here, it can be in here, it can be here. Doesn't matter. But if the object is there in the image, I should send a signal, yes, one. And if it fails to find the object, it will say, no, I have not found it. That is the job. And that is the concept of translation invariant. It doesn't matter where the object is located, how the object is located. Like here, the object may be like this. Here, the object may be like this. Here, the object may be like this. So the triangle, even if it is rotated, like it is one kind, it is rotated slightly, it is again rotated, or it may be here like this. So it doesn't matter whether it has been rotated or not, whether the size of the object is big or the size of the object is very low. So it doesn't matter whether the size is increased or not, whether it is rotation, transformation invariant. Okay, so the object should be recognized irrespective of its location, that is called translation, as well as it should detect the object whether it is being rotated as well as scaled down or scaled up. Here in this example, suppose in this example, I want to find whether the image contain a bird or not. Now, initially, if we try to find the bird in the image, it will be very difficult job for us. How to find a bird in a dark? So, rather, instead of finding initially the bird in the image, let us try to find out the attribute of the bird in the image. And after that, add up all the attribute to come up with a decision. Like what are the attribute of the bird? A bird having a bird having a beak, a bird having a specifiedly designed eyes, a bird having a claws, which is again specifically designed, and the bird is having a very nice, beautiful feathers. Different design, different shades of feathers. So these are the unique criteria by which we may identify a bird. So it is also having a unique eye, a beak, a nice claws, nice designed feathers. So it looks quite attractive, I must say. But in this example, I need to find a bird, and before finding the bird, I need to get this attribute. If those attributes are there all together in an image or are assembled in a proper place, I can come up with a decision. Yeah, there is a bird in the image. So that is what we need to achieve in there. So it doesn't matter. So again, I may erase this slide. So it doesn't matter whether the beak is at the top left of the image or is at the center of the image. So it doesn't matter where the beak is located. My job is to find it out. So that is the property of translation inquiry. It doesn't matter where the attribute is there. My job is to find it out. So beak is the upper lip position, beak is the middle position. It doesn't matter. I have to find it out. Next is the locality principle. Okay. Locality principle, by that means I can go to the previous slide and talk about it. Suppose when I am looking for the beak of a bird, I am searching for the beak of a bird. So I should see the whole image and see whether it is forming a beak or not. Rather, I will look into a local region and try to find out the beak of a bird. So if you want to search for something, you need to search locally in a concise small region. I need to find out the object rather than looking into the whole picture and try to find out whether it is there or not. So I can run a small window like this. As you can see in this example, I am using a horizon. I am using a rectangular window. Now this window will move throughout the image or hover throughout the image like this. Like any scanner, it is going to scan throughout the image and try to find out whether the beak is there or not. So whenever this rectangle will find out the beak of the bird, it will send a high signal like metal detector. It will keep on buzzing. I find out the beak of the bird. And in these places, it will send no signal because it has not found the beak of the bird. So rather than seeing the whole image altogether, we will look upon each local position of the image and try to find out whether it has find out the beak or not. And it will keep on searching throughout the image in a sliding window like manner. So this is the concept which is called the locality principle. So focus on the local region without regard to the content of the image in distant region. Suppose in a crime scene, you want to look for any blood thread or not, you want to look for any knife there is or not, or any gun is there or not, or any gunpowder there in the room or not. So you will not see the whole room try to look for these objects. Rather, you will use some lenses and try to zoom in each scene to detect whether there is any crime object is there or not, isn't it? So it is like I want to detect each position of the image separately and try to find out the object is there or not. That is the locality principle. Rather, after that, we'll aggregate this local representation to make the prediction as a whole new level. So firstly, like we'll find out the beak, then we'll find out the feathers, then we'll find out the claws, and after that, we'll find out the eyes. So, and we'll add up all those pictures and we'll come up there is a bird. So, please ignore my drawing, but this is how things can be done. Now, traditional machine learning algorithms on neural networks was good, but there were some limitations. They were not good at predicting things because they were losing out these regional properties. So we in this class we will precisely discuss about convolutional neural network. This is a neural network or a deep neural network model. This is a deep neural network model which is specifically designed to find any object in an image or in a video. So it consists of the convolution layer, which contain convolution filter. It contain input channel, output channel, padding, stride, and pooling. So these are the crux of any CNN model. Any CNN model. And at the end of the class, I will give some demo or implementation of how you can achieve or implement this model. So firstly, let me discuss in a very simple manner how a neural network works, though I hope everyone knows it. Like, suppose this is your I feed an image. So this is actually input layer and this is actually an image. Now the image may be, like I told earlier, an image can be a 30 cross 30 pixel. An image can be a 30 cross 30 pixels. So 30 cross 30 is how many pixel is there? There are 900 pixels. So there will be a 900 number of nodes will be there, and each node will have a value. So there are how many nodes are there? From node 0 to node 899. These many number of nodes are there, and each node is representing a pixel. Now these nodes, if it is a grayscale image, then these nodes will have a value in the range 0 to 255. For simplicity, I am talking about the grayscale image. So these are the possible values of each node, and this is my input layer. After that, it will go through multiple hidden layers, like the concept of any neural network. It will pass through each hidden layers and come up with the output layer, where output layer will say, yes, the boy is present or the child is present in the image, or no, there is no child present in the image. That is the final decision it needs to make. It is sometimes look as a black box where you feed the image. So this is the image I am feeding, and it is giving me a response whether the child is there or not. That is the image. That is the basic concept of any neural network. But feeding the image in a neural network model like this manner, it is not good. And that is why we come up with the concept of convolutional neural network. So earlier neural network, we used to feed the image like this. So if it is 30 cross 30 image, then total 900 pixels are there. We basically flatten in a one direction and we used to feed them like this. But suppose this is your image. So obviously for this particular pixel, these are their neighborhood pixels. These are their neighborhood pixels. So obviously this pixel having some closeness or neighborhood relationship with these pixels. So with these pixels will have some similar nature or characteristics or color shades. Na? So this is one important thing which we were missing out in case of conventional neural networks. And that is why we come up with a convolutional neural network that takes care. We need to feed the image as a two-dimensional entity only. We cannot feed the image to any neural network model as a one-dimensional entity. Rather than we must feed the image in a neural network as a two-dimensional entity. Let me again point it out. Like in an earlier neural network, what happens? This is your input layer. This is your hidden layer. For simplicity, I am suppose considering there is no only hidden layer. And this is your output layer. Huh? There is a full connection between input to hidden layer, and there is a full connection between hidden to output layer. So this is input layer, this is hidden layer, and this is output layer. Output layer, maybe there is only one node. If it is zero, then maybe the object is not present. If it is 1, then the object is present. It may be simple. So these are the 900 pixels I am feeding. This is my image. So image I am feeding in a conventional neural network as a one-dimensional entity. 900 values are there in a single vector, and I am passing it to the hidden layer, and from hidden layer it is going into the output layer, and if the output layer value is 0, then no object is present. If the output layer value is 1, then the object is present. But now this, as we are using a single column vector to represent the input layer, it is affecting the performance. Rather, CNN telling feed the image as it is, like feed the image as a two-dimensional entity. So what I am suggesting here, that now input will not like a vector, column vector, it will look like a matrix. It look like an image as it is. So this will be now my input layer. Obviously, if input layer is a 2D grid, hidden layer should also be a 2D grid. So from input layer, there will be a full connectivity to the hidden layer. And after that, there will be output layer, and output layer can be a single byte. If it is 0, then the object is not present. If it is 1, the object is present. And there is a full connectivity. So this is hidden layer. What is different between convolutional neural network and the traditional neural network like multi-layer perceptron? Earlier, it was a column vector, a single dimensional entity we were feeding. Hidden layer was also single dimensional, like column dimension. But here, input is two dimensional and the hidden layer is also two dimensional. Like this is the input representation, this is the hidden representation. Obviously, instead of this is grayscale image, in a color scale image, obviously, suppose this is your 30 by 30 image. Now. Suppose this is your 30 by 30 image. Now, this is your 30 cross 30 image. Obviously, and hidden representation not necessarily will be 30 cross 30. Suppose hidden representation is 50 cross 50. This is for grayscale image. But instead of grayscale, if it was a color image, so there will be one matrix for the red. A similar type of matrix would have been there for the green. And let me choose a different color or better perception maybe. So there will be another matrix, maybe blue one for the blue one. So now how many matrices are there? So obviously these pixels, each with respect to red color, green color, and blue color. So this will be your input representation. Now input will be a three-dimensional entity, not two-dimensional. Similarly, the hidden representation should also be a three-dimensional entity. So it will be 50 cross 50. And suppose you are generating 5 such matrices. Then in that case, the hidden representation will be 5 cross 50 cross 50. So here input is three-dimensional and output is, sorry, hidden representation is also three-dimensional. So here input is again three-dimensional entity and hidden layer is also three-dimensional entity. And this is how we are coming up like input should be one-dimensional, hidden representation should be one-dimensional. We basically coming out of this restriction, now input can be of any dimensional and hidden layer can be of any dimensional. That is the novelty of convolutional neural network. I hope up to this point everyone is aligned with me conceptually. Now I am not going into the mathematical detail, but in a simple term, I would like to say that in a normal MLP, what happened? In a normal MLP, there is an input layer. So input layer multiple nodes are there, which are basically input values. And there are a lot of hidden layers are there. And finally, there is an output layer. So each input node is connected with every input node is connected with every hidden node. So here you can see in this picture, all the input node is connected with all the hidden nodes. Similarly, all the hidden nodes are connected with all the output nodes. So this is input layer. So input layer, all the nodes we call the input nodes. In a hidden layer, all the nodes we call the hidden nodes. And in output layer, we all call all the nodes as an output node. So obviously, there's a full connectivity. But it was a simple one-dimensional architecture. It was a simple one-dimensional architecture. Now here is a two-dimensional architecture. It is also must be a two-dimensional architecture. In that case, the here how you can represent the inputs like input 1, input index 1, input index 2, input index n. This is how we represent inputs if it is a one-dimensional. Like this is hidden value 1, this is hidden value 2. This is hidden node 1, this is hidden node 2. This is the output node 1. So there is only one subscript was there to represent the index if it is a one-dimensional entity. But as the image is now two-dimensional, so I am using two index, K and L, to represent its position in a two-dimensional system. Similarly, I and J, it is the hidden representation, like pixel position in a two-dimensional space. So obviously the weight connecting, suppose this input node, this is the input node I. Input node I is supposed connect with this hidden node. Suppose this input node connected with hidden node. So what is this input node? Input node is IN and hidden node is H2. So what obviously this weight which is connecting this input node and the hidden node, this weight will index by 2, which is the index of the hidden node, comma N. So W is the weight or the link weightage between the hidden node 2 and the input node N. This is the concept. So obviously here input is two-dimensional entity and hidden is also two-dimensional entity. So the link, this link which is connecting these two nodes between input layer and the hidden layer, these are the index of the hidden layer and these are the index of the input layer. And this is a unique value. So for each combinations, like if this input node is connected with these hidden nodes, similarly, if the index of it is A, B, and if the index of this is X, Y, then obviously the associated weight will be represented with X, comma, Y, comma, A, comma, B. And this is how we will have a set of weights which is connecting each input with each hidden layer. So obviously we will come up with a weight matrix, which is connecting all the input nodes with the all hidden nodes. Now, previously I talked about the property, like it should be translation invariant and it should also be a locality principle it should follow. Like if I want to make a relationship between this hidden representation and this pixel maybe. So obviously for computation of this hidden representation, I am not going to consider this whole image. Rather, I am just going to consider a neighborhood of this pixel. So this is called the locality principle. For the computation of hidden layer, we are not going to consider all the pixels, rather than we are going to consider only the neighborhood pixels. Let me try to explain it in a very simple way. Suppose you are working with a normal neural networks. These are the input layers, the 4 input nodes, 1, 2, 3, 4. And suppose this is your hidden node. So this is X1, X2, 3, X4. This is the hidden node 1. So all are connected now. This will be W, hidden node value 1, 1. This will be W1, 2, hidden node 1, input node 2. This will be W1, hidden node, 3, input node, and this will be W1, 4. Am I right? So in this case, for the computation of the hidden node 0, for the computation of the hidden node, for the computation of the hidden node 1, I am considering all the input nodes. So the hidden node output, this is the hidden node output. So what will be the hidden node output? Suppose I am representing the hidden node output as, one second. Suppose I want to represent the hidden node output as something like S of H1. Suppose this is the output of hidden node 1. So it will be a simple sum over of I equal to 1 to 4 X I W1 I. So this sum over value will be the obviously on the top of that I am going to apply a function S, and this is going to be your output. Now this S function can be any function, like suppose the S function is like this. So Sx is 1. If it is Sx is 1, if it is greater than, like if Sx is greater than 0.5, then it will be 1. And if the Sx is less than 0.5, then it will be 0. If the Sx is okay. Let me erase this part. Here it is not so clear. Okay. So what I wanted to say, let me write in here with a different ink. So suppose what I mean to say that you are doing a sum over of xi and output of hi, it will be, I should write sum over of I is 1 to 4 xi w1 I, and if this sum over is maybe more than 0.5 or less than 0.5, based on that its output will either be 1 or its output either be 0. So this you can consider S can be any function. Here you can consider S is a function, something like that. So here I should write, instead of H, I should write output of H, OH. So got my point? My point is to whatever input is coming into X, so this is the net sum, Xi into W1I. This is the net sum. This is the input to the hidden node. That is, I mean to say, this is the input to the hidden node. So input to the hidden node is this one. I have discussed a lot of things. For simplicity, let me just, in a one line, let me solve it. This is x1, x2, x3, x4. So these are my 4 inputs. This is my hidden node. And these are the corresponding. This is the H1 is the hidden node 1. Now, this is the H1 is the hidden node name, H1. So what will be the input to this hidden node? The input to this hidden node will be sum over of I1 to 4 xi w1I. This is the input to the hidden node. And there is some activation function is there in any neural network. Activation function. There is some activation function in a hidden layer. Now in an activation function, the simplicity activation function I am telling you that if this input is less than 0.5, then the output, if this input is less than 0.5, in that case, S of this thing, sum over of I 1 to 4, xi, w1i, it will be, if it is less than, then it will be 0. And if it is greater than 0.5 or greater equal to 0.5, in that case, this implies sum of this thing will be 1. Are you people got my point? So the input to this hidden node, this is the net input, weighted input to the hidden node. If it is less than certain value, then the output will be 0. If it is more than certain value, the output will be 1. But reality, we use lot complex activation functions, which precisely we use the ReLU activation functions, which says that, okay, ReLU is another important point I think I should discuss. Suppose your input xi, w, 1i. If this value, is less than 0, in that case, the s of this will be 0. And if it is greater than 0, if it is greater than 0 or greater equal to 0, in that case, the output s of this will be just this value, like sum over of whatever be the value, I 1 to 4, xi, w1. So this is called ReLU activation functions. So in general, in a convolutional neural network, we use ReLU activation functions. But what was the point of view of this discussion? Like if I want to compute a hidden node value, I need to consider all the input nodes to compute the hidden node values. But in case of convolutional neural network, for computation of this hidden node value, I am not considering all the pixels. Rather, I am considering only this set of pixels. So earlier I could have considered only these 2 pixels to compute this hidden node value, but I have not done it. I have considered each and every pixel to consider this hidden node value. To compute these hidden node values, I have considered all the input nodes. I have not considered a set of input nodes. And that was the limitation of normal neural network. But in case of convolutional neural network, for the computation of this hidden node value, I am considering only this subset of input nodes. Locality input nodes I am going to consider. Like if I want to look for a crime scene, you will look for only the region specific to it, whether it is there or not. You are going to ignore these parts. That is the point of view of convolutional neural network. Locality principle. For computation of any hidden node values, I am not going to consider all the input node values. Rather, I am going to consider a few input node values. This is the concept. So rather than considering all the inputs, I am considering the fixed set of input within this range. That is the locality principle. There is another concept is there, translation invariance, like I'm not going into the mathematical detail. I have already talked maybe little bit about mathematical detail. So let me pictorially explain it. Suppose you want to look for the beak of the bird. It doesn't matter where the beak of the bird is there. So if you look into this earlier equation, this is the weight. This is the weight which is connecting this input node with this hidden node. This is the weight is connecting this input node with the hidden node. But for the computation of this, I should make, suppose I want to compute this hidden node value. I should ignore what is the input values, input pixels in here. So I can come up with a better representation like this. For the computation of the hidden representation Hj, for the hidden node at the position, for the computation of the hidden node Ij, for the computation of the hidden node Ij, I should ignore this thing. I should ignore the input index. So your hidden representation should be independent of the input positioning, and that is called the translation invariance. So basically, our ideal representation should be look like this. So your representation, as you can see in this picture, for the computation of the any hidden node, we are ignoring the input positioning, we are ignoring the hidden positioning, and we are basically only focus the range of the pixels which we are going to consider for the computation of the hidden node. That is what our objective is. So in a previous pixel, the input position was ij. In the next pixel, it is position is pq, but it doesn't matter. The weight is same. So you can consider it is like this is the kernel. This weight or weight tensor, this is the kernel. And this kernel we need to learn in a convolution neural network. So suppose you want to look for the beak of the bird. The beak of the bird can be here, it can be here, it can be here. It doesn't matter where the beak of the bird is there. If the beak of the bird is there in the pixel, in the image, it needs to identify it. And that is the job of this weight tensor, or we call the kernel, or we call the filter. So you may have heard this term like convolution kernel, convolution filter, or you may have heard the term like weight tensor. So these are actually same thing. And this is how we make them translation invariance. The location invariance I have already talked about. So here it will look for the beak of the bird in here. After that, it will look for the, so here it has failed to find the beak of the bird. So output of the hidden representation will be 0. In this case, it has find out the beak of the bird, so output will be 1. It is also sometimes known as feature detector. It needs to detect a feature. Here also output will be 0 because it has failed to find the beak of the bird. So here, peak detector. So our convolution neural network concept is what? In our convolution neural network, we need to apply a lot of kernels. The crux of CNN is that in a convolution neural network, we need to apply multiple kernel, and each kernel is a feature detector. So I can apply one kernel to find out the beaks. I can apply another kernel to find out the eye of the bird. I can use the third kernel to find out the feather of the bird. I can use another kernel to find out the claws of the bird. And in this way, I can apply numerous number of kernels to find out all the properties of the bird. And if I find out all the properties of the bird are present in the image in their designated position, in that case, we can come up with the answer that the peak of the bird is, the bird is present in the image. So this is how it works. This is your input layer, which can be like this. This is your output or hidden representation, and this is your kernel. This is your kernel, which try to look for the beak of the bird. It can be called the beak detector. In generic sense, it is a feature detector. The feature can be any like beak, feather, claws, eyes. So this is a feature detector, which we also known as kernel, also known as filter. And if it is find it out, then it will send a high signal, I have detected it. And if it fail to find it, it will send a low signal, I have not find it out. Okay. Now input change. Till now I was talking about grayscale image, But input shape can be three-dimensional. Like this is the height, this is the width, and this is the number of channel of the input image, red, green, and blue, 3. So hidden representation will also be 3, like I have told earlier. And the output representation should also be a 3. So how convolution works? Let me come to this picture. Suppose this is your input image, and this is your input image, and this is the kernel or weight tensor or filter you are going to apply on the input image. So this is your kernel I want to apply on the input image. So I will apply first in this region only. See, in this region only I am going to apply. So I will apply and make it a dot product. So this will be multiplied with this will be multiplied with this will be multiplied with this, and this will be multiplied with this. So it will come up with the value 19. So I will get a value 19. Similarly, next time this window will be moved this side, it will be compared with all these pixels. It may be come up with another value. Fine. After that, this kernel will be multiplied with this pixel. It will come up with a value which we are going to say this is earlier value like x2. This is x3. And after that, this will be multiplied with this part and it will come up with the value of x4. This is how values are obtained. I have a animation for it. So it will be 19. After that, it will be multiplied with this box. And it will going to give a value like 25. So 25. Then it will be multiplied with this part. So this part will be multiplied this into this. So it will be 37. And finally, it will be multiplied with this part and this part. So it will be this and this. It will be 43. So it is your input image after applying the weight, tensor or the kernel, any name you can use, kernel or filter. You are going to get this output. So here one is that after applying this filter, earlier the input resolution was 3x3. After applying the filter, input resolution become 2x2. Sometimes I say that we should not change the input resolution. Like I want output also to be 3x3 only. So there are certain trick to do that. Let me talk about that tricks. This is my input image. It is 3x3. This is my kernel or filter or weight tensor, whatever you say. It is 2x2. So output image size will be like this. So input height 3, input kernel height -2 plus 1. This will be your output height. So 3 minus 2 plus 1, it will be 2. Similarly, what was the width? Width of the input was 3. Width of the kernel was 2 plus 1. It will again be 2. So output image will be 2x2. That is the formula. Output is 2x2. Now let us assume that this is your image. This is an image, and this image you can consider detect the age of an object. So I want to find out the age in an image. So you can consider there is an age there in the image. There is an age because these pixels, suppose these are the black pixels. Suppose these are the black pixels. All are black pixels. Suppose these are again the black pixels. So obviously these are black pixels, these are white pixels, and these are again black pixels. So obviously there is one edge there. So these are black pixels. These are the black pixels, and in between there, these are the white pixels. So obviously there are some edges are there in the image. These are the edges in the image. Now your job is to find out or detect the edge present in the image. How we are going to do that? So I am not asking a complex task like find the beak of a bird. It will be difficult. Try to find out the beak of the bird in an image. It can be tricky. But a beak of a bird may consist of multiple edges. Like suppose this is the beak of a bird. Suppose this is the beak of a bird. So it is an edge. It is an edge. You need to find out the beak of a bird in a pixel. So this beak of a bird consists of three edges. Edges 1, edges 2, and edges 3. So beak of a bird consists of three edges. So if we can find out these three edges, we will be able to find out the beak of a bird. So here similarly, so in any image classification, our first job is to find out the edges present in an image. Now in this image, these images look like what? These images look like there is some black pixel, there is some black pixels, and in between there are a lot of white pixels. So in this example, I need to find out these two edges. How we are going to detect the edges? For that, I need to have some kernel. So I need to have a weight matrix or kernel to detect these edges. So this is my input image. And I am going to use this kernel. I am going to use this kernel. And I am going to find out the edges. So this is the kernel I am going to use, 1 minus 1. So input image is this and kernel is 1 minus 1. I will apply it on the on this particular input and I will come up with certain set of output. See, if we apply this thing, if we apply this kernel over this image, so let me do a task like 1 will be multiplied with 1. So 1 into 1 is 1. And 1 into minus 1 is what? 1 into minus 1 is minus 1. So 1 into 1 plus 1 into minus 1. What will be the output? Output will be 0. So output will be 0. Now I will move this window here. So earlier window was there. Now I will shift this window in here. Now I will multiply. Okay, choose a different color. This color. So now I will multiply this 1 with 1. So 1 with 1. And after that 0 with minus 1. And the output will be 1. So as you can see, this will be have a value 0 and the next value will be 1. If you do this, you will come up with this Y output. So in this way, if you proceed, then you will come up with this. You will come up with this matrix. And in this matrix, you can precisely see there is an edge. There is one edge and there is another edge. So this is how we can identify the vertical edges in the image. Similar manner, we can find out the horizontal edges present in the image. And if we apply both of these kernels, one kernel for the horizontal edge detection, another kernel is for the vertical edge detection, then we'll come up with all edge detectors. So by applying multiple kernels, I may be able to detect this edge. I may able to detect this edge. Sorry. I may able to detect this edge. I may able to detect this edge. I may able to detect this edge. And by applying all these kernel, I will be finally able to detect the beak of the bird. Now in the previous edge detection, it was a simple. I have applied a kernel 1 minus 1. But reality, kernel cannot be known earlier hand. So based on the data, we learn and try to find out what is the beak of the bird. So there's a one concept called receptive field. Like this was my input image. This was my input image. This was my kernel. I have multiplied this with this with this with this with this. I have come up with the value 19. So for computation of 19, these were the influencing pixels. And these pixels were non-influencing. These pixels were non-influencing. For the computation of 19, these pixels have no contribution. So not they are not important for the computation of these hidden node values or the output node values. So those pixels which take part for the computation of any output or hidden node values, those are called the receptive fields, and these are non-receptive fields. So in case of convolutional neural network, if we had used the multilayer perceptron, we could have used all these pixels for the computation of 9. So instead of CNN, if we had used multilayer perceptron, in that case, we would have used, if we had used multilayer perceptron, in that case, we would have used all these pixels for the computation of these hidden node values. That is the difference with the multilayer perceptron with the CNN. In CNN, we consider only the local inputs to compute the hidden node values. In case of MLP, we consider all the input nodes to compute the hidden node values. So there's a concept of receptive fields, the influencing inputs, where in MLP there is no concept of receptive field in this manner, because in case of MLP, all the input nodes comes under the category of receptive field only. There is no non-receptive field there in MLP. Similarly, for the computation of 288, so if we multiply these, and this, we will get a 288. So for 288, these are the receptive fields in the layer I plus 1, and in the layer I, these are the receptive fields. And these are the non-receptive fields. Whereas in NLP, there is no non-receptive fields are there. Now padding. Padding is another concept I want to talk about. Like this was your input, was your kernel, and previously I told if we apply this kernel on this input image, it will reduce the output image size. So like it was 3 cross 3, so it will be 3 minus 2 plus 1 for the height as well as for the width, so which is 2. That is why the input image was 3 cross 3. After applying the kernel, you come up with an input image which is 2 cross 2. Sometimes we do not want to lose the resolution of the hidden representation. So that time we use the concept of padding. Padding is what? Let me take this image. So I apply 1 0 padding at top, 1 0 padding at the bottom. These are called the padding related to the height because they are applied on the top and bottom. Similarly, we will apply the padding in column, and in that case there is a left and right padding is there. So the input image was 3 by 3. After applying both padding horizontally and vertically, we come up with an image, input image, which is now 5 cross 5, if I'm not wrong.
Sir, what is stride there on your image?
Tell me.
What is the stride?
Stride?
Yes.
Stride, I have not come up. Madam, I had not come up with the concept of stride. I will discuss stride. Till now I am talking about padding. I will jump into stride concept. Just be patient for a few minutes.
Before padding, yes, sir. Before padding, you have to move the stride. First of all, you will go for the horizontal direction, then move for the vertical with the stepwise. Am I right, sir?
Yes.
So whatever is your stride, are you taking the 1 or 2?
I am currently using. Yes, exactly. I am using stride 1, but I have not discussed the concept of stride. I will discuss. It is in my slide. Just be patient. I will discuss. But currently I am using stride only 1.
Yes. Okay.
Because because as you correctly said that this is my kernel. Now I will move the kernel only one position for the next computation. So this is computation of 0, this computation of 3. After that I will move only one position and it will help me to compute this value. After that I will move into that one position, it will help me to compute this value. Then again I will move into the one position only, sorry, yeah, one position only, and I will compute this value. So obviously I am moving this sliding window of the kernel one position at a time, both horizontally as well as vertically. So yeah, stride is vertical slide is one, horizontal slide is also one in this example. Yes, you are right, but I have not discussed this thing. I will discuss this thing maybe after a few minutes, after discussing the padding. Am I clear?
Yeah. But then padding, then mass pool, all these flatten, all these sequentially we should proceed for the CNN architectures. Okay, thank you.
Okay, thank you. So now let me talk about the padding concept. So padding I am applying. So as I was losing out the dimensionality, so I add these things into the image, like one top padding, bottom padding, left padding, and right padding. So input now become 5 cross 5. And after that, this is my kernel, which is 2 cross 2. And I will come up with an output image of 4 cross 4. And as you can see there, again, I can come up with a disparity. Now I have increased the size of the output. So input was 3 cross 3. After applying padding, I come up with an output of 4 cross 4. So that is why I will suggest people to go with the odd number of kernels, like 2 cross 2. Instead of 2 cross 2, use the kernel 1 cross 1, 3 cross 3, or 5 cross 5. So use odd number of kernels. That will help your job. So in this image, just in this image only, instead of 2 cross 2 kernel, if you use 3 cross 3 kernel, then it will solve your problem, because 3 will be your input image, and after if you apply the kernel 3, and after that if you use plus 2 and 1, you are going to come up with the value 3, output image 3. So that is why I suggest to use always odd number of kernel. Else this kind of scenario you may come up. And I intentionally put this scenario so that you can realize the importance of odd sized kernel. So kernel size should be odd always, like 3 cross 3 or 5 cross 5, not 2 cross 2. So as you can see in this picture, if I use a 3 cross 3 kernel, in that case, you will come up with the same resolution. So input was 3 cross 3, the output is also 3 cross 3. If we apply a 3 cross 3 kernel. Because if you apply a padding at top, you must apply a padding at bottom. If you apply a padding at left, you must apply a padding at right. You cannot apply padding in a one side. If you apply padding left, you should apply padding right. If you apply, and the code will also not allow you to apply padding only one direction. If you use the standard libraries, you can manually do that, but that is not never advisable. Similarly, if you apply padding at top, you must apply padding at the bottom. And in that case, if you follow this decorum, you must use a odd kernel to make sure that you are coming up with the same resolution in the input layer as well as hidden or output layer. Now, I need to talk about stride. Like I told earlier, I am just going to talk about stride after the padding. So padding is now clear. Now, let me talk about the stride. Like, yeah. So till now, I was talking about stride 1. Now stride width 2. That means this is my kernel. This is my window. I will multiply them and I will come up with a value like 90. Now, I will, okay, use a different ink like blue. Now I am not going to conceive moving the window this position. Rather, I want to directly jump into this position. and I want to compute the output. So I am skipping this window. So I am sliding 2 position. In a widthwise, I am moving 2 position, not 1 position. And that is why the stride width is 2. Earlier stride was 1. I was moving 1 position at a time in a horizontal direction. Now I am moving 2 position at a time. That is why stride width is 2. Similarly, length stride 2 means what? I will consider this window and I will consider this window. So earlier maybe I am in this position, now I will be in this position, the starting position. So I am moving 2 stride at a time in a vertical direction or lengthwise direction. So I am basically ignoring this window. So in this example, this is maybe 1, this is 2, this is 3. From 1, I am directly jumping into 3. So here the stride length is 2. So if you go like this, you will come up with a pixel like this. So this is how you are going to achieve. Now, what are the advantage of stride and what are the drawback of stride? So if you are going to use stride 1, it will make sure you are not losing out any information, because in this example you may have noticed I have not considered this window. 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 So somehow I am skipping these informations, and these informations may be vital. That is why it is advisable not to use stride more than 1. But sometimes the image may be very high resolution, like nowadays. Nowadays the input resolution can be 980 cross 1240. The HD images or super HD image, 4K images. These images having too much resolution. Now, if I go back to my video architecture, suppose your video is of 1 minute. So 60 seconds is there. Now frame per second. It can again be 60 frame per second. Now your maybe it is a RGB image. So each pixel will be represented with 3 bytes. After that, if it is your resolution is 980 cross 1240, if this is your resolution, then a particular video will be very high sized. And on performing any image processing task to find out any child in that video, it will take a lot of time to compute. It may take 4 to 5 minutes to compute whether there is any child is there in the image or not. It will slow down overall computation or detection capability, slow it down. So you will come up with a result, maybe a correct one, accurate one result, but it will take a lot of time to get the result. That is why people suggest that if your image resolution is too high, then you need to downsample the image. Downsample means quickly reduce the image resolution without losing much information. That is the concept of stride. So use the stride wisely when the image resolution is high and you need to get the output quickly. You should not delay in getting the output. That time you should use the stride. Stride is not for getting a good result. Stride is good for getting a quicker result. It downsample the image. Downsampling means quickly reducing the resolution of the image. And this is how stride works. So stride drastically reduce the resolution of the image. Like in this image, input was 4 cross 4 and kernel was 2 cross 2. And you have come up with the output which is 2 cross 2. So it has half the size of the image. So if it was 20 cross 20, it would have been drastically reduced to 10 cross 10 image. So that is the benefit. It quickly downsample the image, save a lot of time for us, but it may compromise with the efficiency or accuracy of the model. Stride larger than 1, reduce the dimensionality of the output feature map. This come at the cost of being sloppy in determining whether the feature exists or not. So it can hamper the accuracy. A layer with stride more than one might skip the location where the feature is actually present. Like micro expression classifications, like in criminal psychology, we try to detect the video of a person or try to find out whether that person is basically intentionally. Sometimes polygraph test is banned, na? So we cannot perform polygraph test. So how we can understand someone is lying or not? So in that case, we try to detect the micro expression. Maybe he is saying something wrong, but some micro expression reflexes he may show, a criminal may show, which may indicate that the person is lying. So it is a alternate way of testing whether someone is lying or not, lie detector. So you can use micro expression detection. So in those cases, it is not wise to lose out information for the just take off for the getting the result very quickly. So that is why so every time study is not advisable. More than one study is not advisable. So RGB image, now input channel. Let me take an image. Suppose for simplicity, I have considered the input image is obviously in case of RGB, the input is 3 cross 2 cross 2. For simplicity, I have considered the input image is 2 cross 3 cross 3. So 3 cross 3 is the height of the image, width of the image, and maybe I have considered only the red channel and the green channel. I have ignored the blue channel for the simplicity. This is your input image. So this is the width of the image, this is the height of the image, and this is the channel of the image. So input is now 2 channel image which having this width and this height. So obviously if the input is of 2 channel, the kernel should also be of 3 dimensions. So this will be 3-dimensional kernel. No? So this is a kernel which has been applied onto this image. So if image is 3-dimensional, kernel should also be 3-dimensional. In our case, it is 2 cross 2 cross 2. So obviously this third dimension, the channel dimension of input and the channel dimension of the kernel should always be same. Input dimension may be 3 cross 3, 100 cross 100. Kernel can be 2 cross 2, 3 cross 3. For simplicity, I have kept it 2 cross 2. Because its representation and mathematically representation will be difficult in the slide mode. So that is why I kept it low 2 cross 2. But I always suggest go with the kernel odd size like 3 cross 3, 5 cross 5, etc. So in this example, how I'm going to apply this kernel will be applied in this part of the image. Maybe this kernel related to the red channel. This kernel may be related to the green channel. So this kernel will be applied on the green channel. After that, so I will apply this red kernel with the red channel, green kernel with the green channel. After that, I will add them up like I have done in here and will get an output value. See how it is working. So I am going to apply this kernel related to the red channel. We'll get some output. I will apply the green kernel with the green channel, get with the some output, and I will add them up and get a value 56. So I will write 56 in here. Similarly, I will do apply in this part, apply in this part, apply in this part. Similarly, for the green channel, apply in this part, and going to come up with this value. So as you can see in this image, the input was 2 cross 3 cross 3. So input was 3-dimensional. This is a channel dimension. This is the height and width. Output is what? Output is 1 cross 2 cross 2. So this is the resolution of the output image, which is 2 cross 2, width and height, and output channel is 1. So we are losing out the channel information. So if the input channel is multidimensional, like in this example, input is of 2 channel, the output should also be of multi-output channel. So output should not be 1 channel. I hope I am clear to everyone. So input, if the input having multiple channels, multi-input channels like red, green, blue, output should not be a 1 channel. Output should also be a multi-channel. So that is why I will come up with, so if I can use, this was a 3-dimensional kernel. Now, It was a three-dimensional kernel, 2 cross 2 cross 2. If I can apply a similar 2 cross 2 cross 2 kernel, if I apply another 2 cross 2 cross 2 kernel, which may give me another output channel output, like 1 cross 2 cross 2. And if I can cascade them this with this, then I will come up with a multi-channel output. I hope I am clear to everyone. So my input channel was two-dimensional. After applying this kernel, I got a output channel 1. So what is the easiest solution? Similar to this, I can apply multiple kernels. So suppose I want to apply 3 kernels, kernel 1, kernel 2, and kernel 3. So for all the kernel, I am going to get a matrix like this. So for, let me use different kernel. It will simplify things. So this kernel giving this output, channel 1. Apply another kernel. Apply another kernel on this image. You will get another output representation, so another channel. Let me apply another green one. So I will apply another kernel on this input image. I will get another channel. So how many output channel I get? If I cascade them, I will get 3 output channel. So after applying multiple kernel, I can come up with multiple output channels. That is the very important thing in a convolutional neural network. In a convolutional neural network, we should always increase the input channel. So if input layer, if the number of channels is 2, I should keep on increasing to maybe 3, 16, 96. So we should keep on increasing the number of output channel, because these channels are basically trying to detect different features. Like this kernel may be trying to detect the beak of the bird. This may be trying to detect the feathers of the bird. This may be trying to detect the claws of the bird. So each kernel trying to detect a different feature of the bird. And after that, we will aggregate them all up. So number of output channel we need to keep on increasing. And for that purpose, we need to apply multiple kernels. And in a mathematical sense, multiple kernels means here we are using 3-dimensional kernel. Now, I suggest to go for 4th-dimensional kernel. So this kernel I need to apply n number of times to get n output channels. So my kernel should be a 4th-dimensional entity. If my input is a 3-dimensional entity, my kernel actually should be a 4th-dimensional entity. Then you are going to get the n number of output channels. So in a kernel, these will represent the width, these represent the height, these represent the number of input channel, these represent the number of output channel. In the next demonstration, I'm going to show it. So this was my input image. This is the kernel. This is the output channel 1. Similar, I am applying another kernel. I am on the same input image. I am getting output with respect to a different output channel. So obviously, in that case, the kernel is a 4th-dimensional entity, where this is the number of output channel, this is the number of input channel, this is the height and width. Now pooling. Pooling is another concept. So now I hope the convolution layer concept is clear to everyone. I need to apply the kernel on the image. I cannot apply the kernel on the total image. I will apply the kernel on a certain section of the image. And I have discussed about both how it can be applied on grayscale image and how it can be applied on color image, and how I can come up with a multiple output channels. Till now that I have covered. Now pooling is another concept in CNN that I want to cover. So pooling, suppose this is the output. So you let me use a different name. Suppose this was your input layer. You applied some kernel to come up with the output layer. Now this is the output layer. This is the output layer. Now this output layer, I want to use a concept of pooling. Pooling is doing what? Pooling, there is a 2 type of pooling. One is max pooling and another one is average pooling. So this was your input layer. I apply a kernel, I got a output layer. And this output, on the top of this output layer, I want to apply, on this output layer, I want to apply pooling. So pooling, max pooling says, max pooling also come up with a window. So pooling also come up with a window. In this example, I have considered a window of 2x2. So I will use a 2x2 window, pooling window, and max pooling says pick the maximum value within the window. So in this window, the maximum value is 5. I'm going to pick 5. After that, I will move the sliding window 1 horizontally. So I will come in this part. I will pick the maximum value, which is 6. Then vertically, I will move down in a one slide or one stride, and I will pick the maximum value, which is 8. Then I will move the slide horizontally again, and I will pick this window and pick the maximum value 9. So after performing the pooling, the output will look like 5, 6, 8, 9. So this were input. After applying kernel, this is the output we will get. And one output after applying the max pooling, this is the output you will reach. Similarly, instead of max pooling, if you apply the average pooling, then we will take the average value of these 4. So 1 plus 2 plus 4 plus 5 by 4. So 1 plus 2 is 3 and 9 is 12 by 4, it may be 3. It is 3. So this is how average pooling works. Now I suggest everyone to go for max pooling, ignore average pooling. Because max pooling is always going to give you good result. Okay, if we ignore the exceptions, you are going to get a good result in max pooling only. Okay, why pooling I have used? Now people may ask why I was using kernel because I want to detect the features. So kernels are nothing else but the filter or feature detection, helping me with come up with the features. So that is why I was using kernel. Now why I am using pooling? So pooling is used to help me with the location invariance. Like suppose whenever we are taking some images, some pixels may be move out. What I can say, like the pixel was 5, 6, 8, 9. Some distortion, this 8 can become 9, and with some distortion, this 9 can become 8.5. This 5 can become 4.5, or this 6 can become 5. So these many changes may happen, na? So if you apply a pooling, it is make sure this distortion or changes can be correctly addressed, and that is why pooling is used. So pooling and location invariance. Suppose this was my original image, and suppose this is my altered image. Due to any problem, this pixels has been suffered. The in place of 0, 1 comes, and in place of 1, 0 comes. So this is my altered image. Now, if I apply the pooling, you are going to, if you apply the pooling in this window, and if you apply the pooling in this window, you are going to get a same value, irrespective of location invariance. So pooling make our model location invariance. Even if there is any problem with location in your data output, pooling can handle it. And that is why pooling should be used after applying convolution. And I suggest go for max pooling. So pooling does what? Suppose it has found out the beak of the bird. It will give a high output value. Yes, I have found out the beak of the bird. In case of max pooling, it will pass the maximum value. In case of average pooling, it is pass the average value. I suggest always go with the max pooling. So if you have find out the beak of the bird, your indicator or buzzer may buzz as much as possible so that people can find it out. And if it fail to find the beak of the bird, it should find a low value or it should not pass. So that is why you must go for max pool. The pools are usually quite small, so you would still know fairly accurately where the feature is located. Now, suppose I want to use the whole window. 1 second. Huh? Hello. I am currently outside. You can come to my room and knock. Huh? You come to me, knock and deliver the product. Huh? C block 304. 304. नहीं नहीं नॉक करके घर में दीजिएगा. You want to deliver the product, no? Hello, sorry everyone. Extremely sorry, I got an emergency call. So I think I am still aligned with everyone. So that was the job with that was the problem with pooling. That if you increase the size, okay, am I clearly audible to everyone still now?
You are audible. Please carry on.
Yeah. Yeah. So what I was talking about that suppose you want to use the whole window for pooling. Suppose you want to use the whole window for the pooling. In that case, you cannot. You will go if I use the whole window for the pooling. I will obviously find out the beak of the bird is present, but I may not know which position the beak of the bird is present. So that is why it will wise to use a low pooling window so that even after finding it out, I should know where exactly it is present. So you should not use the pooling window more than 3x3. So how it actually works, let me see a picture. So suppose you want to find out the cat. If the cat is moving in front of my car. So I will apply the convolution. So convolution layer come up with a kernel and after that an activation function. Activation function always go for the railway activation function, which I have discussed. So you will apply kernel after railway activation function in the convolution layer. After that, apply max pooling layer. This pair you can apply multiple times. When it will be done, you will flattening them. Flattening them means how? Like suppose your final layer is like this. Final output layer, penultimate output layer look like this. So this is a grid. How you are going to flatten them? So maybe you can take all these like okay. Instead of this, I should use symbol values 1, 2, 3, 4, 5, 6, 7, 8, 9. So if you flatten it, it will look like 1, 2, 3, 4, 5, 6, 7, 8, 9. This is how it will be. So I will flatten them and after applying a simple MLP or something to find out the cat is present or there or not. This is how a simple work, and this is a limit. It is a It is a convolutional neural network. As you can see in this example, the input image is grayscale image. So it is a 1 cross 28 cross 28. 1 means the input channel is 1. This is the height. This is the width. After I am applying a convolution layer, and convolution layer, the number of output channel is 6 and output resolution will be 28 cross 28. After that, I am applying a pooling where the output will become now 14 cross 14. After I am using another convolution layer, which is number of output channels 16, the output resolution will be 10 cross 10. After that, I will apply a pooling because always after convolution, apply a pooling. So the output will become 16 output channel 5 cross 5. After I have using the flattening layer to flatten it. After that, one hidden layer and output layer. This is a simple multi-layer perceptron. So this is how, this is the input image. After that, I have applied a convolution KNN kernel. Convolution kernel is 5 cross 5 kernel I have applied. Number of output channel was 2. Padding I have used 2. So the resolution of the output image will be number of output channel 1. Number of output channel will be 6 and it will be 28 cross 28. After that, that time average pooling was there. So he has used average pooling, but I suggest everyone to go for max pooling. And this was the pooling window 2 cross 2. Stride was 2 because in pooling, you can increase the number of stride. After that, again, a convolution neural network has been applied. So where the kernel size was 15 cross 15, 5 cross 5, and the output number of output channel was 60. After that, you apply another pooling layer, which is average pooling. The pooling window is 2 cross 2, stride is 2, and this is will be the output image. So number of output channel is now 16, 5 cross 5. After that, this is the fully connected layer, flattening layer, and it will flattening them. So it will be the, there will be only one channel, and this will be number of node will be 128. So it is like a hidden layer having 128 number of hidden nodes. And after that, again, another hidden layer having 85 number of hidden nodes. And finally, the output layer, which is having 10 number of nodes. So this works on the MNIST dataset. So MNIST dataset having 10 output classes. So 10 categories are there. That is why the number of output node was 10 in this case. So quickly jump into my code. I hope my screen is still visible to everyone. So let me talk about how it can be worked. So the network, lastly, I have shown what that is Lenin. No? So how it can be implemented. So this is my code. Let me share my code with everyone. Internet is quite slow, so bear with me. Please find the chat box. I'm trying to share the detail of my code, so you can directly click and download my code from there. Okay, I don't know, somehow it is not working for me. So chat box is not working. The question answer window is working or not?
Please share it to me in WhatsApp. I am posting in the WhatsApp.
Oh, okay. I will share in WhatsApp. Okay, I will share in the WhatsApp. So currently, let me go to the here. So you can apply this. You can run this code like I have used a Keras library to implementing it. So these are the libraries I need to implement my code. So I need to import Keras. So all the convolution, pooling, code, all are there in this Keras library. So I have imported Keras. And after that, from Keras, I have imported the sequential model, dense layer, flattened layer, max pooling, average pooling, convolution 2D. So, and the MNIST dataset on which I want to apply my CNN model, all I have imported. Let me run it. It has run. Tick means the code has correctly run. Now, number of output class is 10. The input image size is 28 height, 28 width. Number of output channel is 1 because it is a grayscale image, not a color image. Now, for any neural network, the dataset must be divided into the training data and the test data. So this is how I have divided my data into trained data and the test data. Trained data so 60,000 training data is there, and test data is 10,000 test data is there. So this is how images look like. This is how images look like. Now I need to, as you can see, these are not grayscale image. These are the color image, though the color shades are quite different. So what does it mean? It means that the value are not within the range of 0 to 255. The value may be range from 0 to infinite something. So that is why I divided all value with 255 to make sure each value lies within the range of 0 to 255, so that I can use only one byte to represent a pixel. So after that, the number of training sample is 6,000, number of test sample is 10,000. After that, this is how anyone can implement a convolution neural network. First of all, you need to create a model architecture. So model you should be sequential. Why sequential? Because if you can look into my last slide, so a convolution neural network is sequential. So on input, you need to apply the first convolution layer, second convolution layer, first convolution layer, then pooling layer, convolution layer, pooling layer, fully connected layer. They need to apply it on a sequence. You cannot apply parallel. Like you cannot apply convolution and pooling in parallel, or you cannot move their position up. I will apply pooling first, then convolution. You cannot do so, no. You have to apply them sequentially, one layer after another layer, and there is a order of the layers. So that is why you need to have the sequence here. And Keras, this function is there. As you can see from keras.model, I have imported this sequential model. So you can directly use that. You do not need to build on your own. After that convolution, I am going to apply a 2D convolution because input image is 2D. Input image contain only height and width. Input image do not have the channels. So that is why you can use convolution 2D. Number of filters. Number of filter is 6. Number of filters mean number of output channel, which is 6. There was one slide where I told, no, you have to apply multiple kernels to get multiple output channels. So multiple kernels or filters, if you use 6 kernels or 6 filters, you are going to get 6 output channels. And that is why this is the thing I am talking about, is number of output channels. So number of output channel is 6. After that, the kernel I have applied is 5 cross 5. Padding is same. Padding same means what? Padding same means I am going to apply a certain set of padding that need to make sure I am not losing the resolution of the input image. If you look into here, after applying the convolution, the resolution of the image has not been decreased. Earlier input image was 28 cross 28, and after applying this convolution, the input image is still 28 cross 28. So obviously I am not losing out the input resolution. So in that case, you can apply same padding. That will make sure that padding is enough that it is not going to lose the resolution of input image. And that time when LeNet was invented, that time the ReLU activation function was not invented. That is why people have used sigmoid activation function. This is another activation function. So convolution layer, it must have some output channel, it must have a kernel, and you need to be sure whether you are going to use the padding or not. Stride I have not used, that is why stride I have not mentioned. If stride is not mentioned, the default stride is 1 cross 1. If the stride is mentioned, then you can mention 2 cross 2 or 4 cross 4. And activation function is sigmoid. After applying convolution, the next layer was what? Next layer was pooling layer. And pooling, the activation function in pooling was average pooling. So pooling, there is no activation function. In case of average pooling, so that time max pooling was not invented. So that time people have LeCun has used the average pooling, and that is why, to give respect to his model, I have applied average pooling in here. So here the pooling window is 2 cross 2. He has used stride 2 cross 2. I have exactly used stride 2 cross 2, but he has not used padding. He has not used padding in a average pooling layer. and stride 2. So I have also not used any padding. Valid padding means padding has not been used. After that, there is another convolution layer where number of output channel will be 16, kernel size will be 5 cross 5. There will be no padding and activation function is sigmoid. As you can draw this line, here the kernel was 5 cross 5, number of output channel was 16, and there was no mentioning of padding. Similarly, I have not applied any padding. Okay, after that, there was a average pooling, another pooling layer after the next second convolution layer. The average pooling window 2 cross 2, stride 2 cross 2, and there was no padding. Valid padding means no padding. So as you can see, it was 2 cross 2, average pooling, stride size 2, no pooling. After that, I need to flatten them, and number of hidden node will be 120. How I have achieved it? So I have used model.add flatten. It will flatten the all two-dimensional grid into a one dimension. Number of unit will be hidden node or number of unit will be 120. Activation function was sigmoid. After that, the next hidden layer having 84 hidden nodes. So next hidden layer having 84 hidden nodes, activation function was sigmoid. And the third layer is the dense layer. Number of unit, the number of output layer in MNIST dataset is 10. The number of output node in a MNIST dataset is 10. That is why it is 10 written over. And in output layer, I have used softmax activation function. So in a output layer, in a classification model, you should use softmax activation functions. Okay, so let me run it. After that, this will be a model summary that this is exactly what I have written in here. So this will be the layer wise dimension. This will be the number of weights involved in your model. So total parameter size is this. Non-trainable parameter is nothing, and this is the amount of memory your model is consumed. If it is too much, then you need to be vigilant. Like if you are using too many convolution layers, too many pooling layers, too many flattening layers, means dense layers, you need to take care of your memory management as well. After that, you can train your model with the batch size, anything you wish, number of epoch, again, anything you wish. This is the result you are going to get. After that, if you trace your model, you are going to get a good value, I hope. So you are going to, these are the loss, and the accuracy you are going to get a 97% around accuracy you're going to get. If you can increase the number of epochs in there, and I hope you will get a lot better accuracy. But I think it will take a lot of time to run it again. So that is why I have to stop it here. Similarly, you can modify the existing Linnet model. Like it will be difficult for me to move around. Okay, in the meantime, if any are having any question, they can ask me the questions. In the meantime, I will try to see what I can do now. So please, dear participant, if there is any question, please ask me.
If you have any query, please ask him.
Am I audible? Yes, sir.
Yes, you are.
Sir, could you please explain about the dense layer about your model when you are converting the class vector to binary class matrix? So during that, what you use a dense module and how many neurons you used it? Can you scroll down, sir, please?
In this code.
Yes, sir.
Okay,
Yes,
okay, yeah. This part you want to know about.
Sir, yeah.
Okay. So for that, I need to have some editable screen. So let me come into this position. Any vacant space I need to have. So suppose this slide, let me put the slide. So suppose your window, okay. So suppose you're obviously till now you are applying some convolution layers, na? So after applying the last convolution and the pooling layer, after applying the last convolution and the pooling layer, your window may look like this. So it may be, let me consider, suppose it is like 16 cross 5. Sorry, 16 cross 16 or something like that. Maybe 2 cross 16 cross 16. Maybe this is how your uh, final max pooling layer looks like this. Suppose this is how your model look like this. Got my point, now? You are
Yes,
going to
yes, yes.
you are applying multiple output channels, multiple resolution is also changing. So last time after applying the last max pooling layer, maybe this is your input resolution and this may be the number of output channels. So obviously it is 2 cross 16 cross 16. So it will be, if I apply 2 cross 16 cross 16, how much it will be? Okay. So it will be, I think 16 cross 16, maybe 2 to the 512, if I'm not wrong, no? So obviously
Yes, sir.
you need to flatten them. Like after that end of the day, you need to decide, after end of the day, there should be some output layer where you need to say there will be 10 output nodes and you need to say whether it is belongs to class 0, class 1 or class 9. So end of the day, you cannot directly feed. You cannot directly feed a multidimensional grid into the output layer. Because if you know the MLP line of architecture, there is an input layer, there is a lot of hidden layer, and there is a finally output layer. So in output layer, the penultimate layer, which is just before the output layer, the penultimate layer, it should be a one-dimensional entity, else you cannot directly feed into the output layer. And that is why you need to flatten them. So how you're going to flatten them? So suppose for the output channel 1, it is 16 cross 16. So there are 16 row and 16 column is there. You need to write it down in a single dimension, like I have discussed earlier. If the values are like this 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So values, if the values are like this, you need to flatten it like this 1, 2, 3, 4, 5 till 12. No? And obviously, maybe there is, this is the output channel 1. Maybe the next output channel is like 13, 14, 15, 16, till maybe 32. This may be, the value may be look like this. So obviously you are, after that you are going to write 13, 14. So everything will be a single column vector. All values will be there in a single column vector from 1 to 512 or something. Got my point, no? Am
Yes,
I
sir.
clear?
Yeah,
So
yeah, yeah, yeah.
yeah. So this is the last hidden layer, and after that you are now see, if the number of hidden node is 512, this is too much hidden nodes. If you directly apply into the output layer, it cannot perform well. So you need to have some intermediary hidden layers. Like if like people do what now? If the number of input dimension are too many, instead of one hidden layer, they apply 3, 4 hidden layers. Similarly, as you can see in that, where is it? So in this example also, one second. In this example also, you can see the number of hidden node is 128. So if you directly apply it on the output layer, it can have a bad performance. So they have added one more hidden layer just to simplify the learning. So like in MLP also, if the model is complex, we apply multiple hidden layers before applying the output layers. So this is a one hidden layer added upon, because if you can directly 10 after 120, it may have poor performance. And that is why one more fully connected layer has been added. Okay, I hope I answered your question.
Yeah, you're correct. So when we're going for the model building and model evaluation, the input, neurons, hidden layer, depending upon the dense and relative to the activation function, we have to design. Am I right, sir? And it will be the
Yes.
through the powers.
Yes, yes,
Yeah.
that all need to be choose judiciously. And I would also suggest, if you are advanced in these technologies, always use the transfer learning. Means do not build your model from scratch. Take a model already built upon previously, like any available Google Net model or the VGG model, the advanced models, which are already trained with basic data sets. Apply them, just customize them according to your dataset or the need. Do not try to build your model from scratch, because it will take a lot of time to learn.
No,
You
no,
can do
that's
that.
good. Yes. And especially model history also will describe all these, how much you have user past learning experiences, and all these things.
Exact.
Thank
Rightly
you.
said. Thank you.
Okay, so I hope there is no doubt from the participants. Okay, so now we are planning to conclude our second session of the day 5 of our workshop. Thank you, Prasenjit sir, for
Thank you.
giving your presentations, and lot of idea you have shared with our esteemed participants. I hope they have also benefited lot of points. Okay, so we'll share the contents with them also. Okay, thank you for giving us your valuable time. Thank you, Prasenjit.
Thank you. Thank you, sir. Thank you for the opportunity.
Thank you.